problem to me.
So this is the system that we are discussing. We have the signals coming through the antenna into these correlators and into this flux capacitor. And the output data goes into this block, where we have these two flops and the delay elements in it. And to the best of our knowledge, this is the part that's the cause of all the problems.
So can you explain how this delay element block works?
Okay, let me explain how this delay thing works, okay? It basically is controlled by this formula, which we call E equals to mc squared, okay? So here is E is the potential, M is the magnetic field, and C is the capacitance, all right? And so that's how the delay gets controlled.
So where does this E comes to play?
Okay, so that E is basically the potential. Okay, it's the electric charge. It's really the VDD rail on this block, you know?
Great. Now where does the M comes to play?
Well, M is basically the magnetic field, right? And it happens because of the switching current. As the current changes, it develops a magnetic field. And C is?
C, of course, is the flux capacitor. Everybody knows that. Okay, now who did the timing on this block?
Oh, yeah, I closed the timing on this block, but it's solid. Obviously, it's a software problem.
Come on, no way it's such a timing, it's a software problem. It's got to be a timing problem.
It cannot be solved with power problem. Sometimes it shows up, sometimes it doesn't. So it has to be something related to hardware. It has to be a hardware problem.
So it must be a timing problem. Cannot be a software problem. Let's ask the hardware people.
Well, we can easily determine, I can show you the timing closure of this block. So the path here, as you know, is the path between these two flip-flops. We have a 35 nanosecond period. And each one of these delay elements is the same. I tuned each one of them to be 10 nanoseconds each. So each one of these are 10 nanoseconds, and there's 5 of them, so you can see that the timing's easily met.
Okay, so you obviously doesn't agree with what he says. Can you explain it?
This is a problem, okay? I mean, here's 35 nanosecond, and we've got 5 elements. So let's see, you know, what is that we need here, right? Okay, so here's 35, and we're going to divide it by 5, right? So here's 5, and of course it doesn't go into 3.
No. Here, what kind of division is this? I don't know where. Here, let me draw this thing right here. You can draw a line there. Okay, 5 goes into 5 once, obviously. And then there you have the 5, you drop down to 30. And then 5 goes into 36 times. And then 30, there you go. So you have 16 nanoseconds per element. And we're now at 10 nanoseconds. So there's obviously a lot of margin. We have 6 nanoseconds per element of margin.
What are you talking about? No, this is all wrong. Let me show you. Let me show you. Okay. Okay. So let me prove that if you take 16 and multiply it with 5, you don't get 35. Okay?
Yeah, you do.
Okay, let me show you. Let me show you. All right. Here's 16. Okay.
Yeah.
Here's 5.
Yeah.
And multiplying, right?
Yeah, you're right. So we got 5 times 6 is 30. We all know that. Everybody agrees with that. So we got that, and so then 5 times 1 is 5, and we put there, we add 35.
Yeah.
16 times 5 is 35.
No, it's all wrong.
What?
Okay. Multiplication is like adding it, right?
Oh, correct.
So if we take 16 here 5 times,
Yep.
and we're adding, right? 6,
Yep.
12,
Yep.
18,
Yep.
24,
Yep.
30.
Yep. 31, 32, 33, 34, 35. Just like that. Plenty of margin. Software problem.
Okay, I'm convinced that it's obviously not a timing problem. It's most likely a software problem.